Alright, ready to go. So again, before we start with our equations, schematics and solutions, a couple of things that I want to mention. So the first one is that I was looking at the schedule and we are going towards the end. Actually, we have just a few more weeks. Time flies, so we are getting there. So today is April 16th, which means that we have we have this week, so today's class, and then we also have next week, and then we have the meter number 2 the week after, and then after that we will start with the presentations. So also on the 23rd, which is next Wednesday, we have the due date for the presentation. So it is of course one presentation per group, one file per group. I realized that I made the mistake of not having the project as a group assignment, but of course there would have been like one file for every group. I saw that basically everybody submitted, so of course I will look at one for each group. And the same is gonna be for the presentations, of course. So regarding the presentations, I think you should be able to submit either a PowerPoint or a PDF. I would suggest to submit the PDF. I think or if you submit a PowerPoint, probably avoid animations that are maybe too complex, text, the enters, that's not really needed. Also because basically I will have all the presentations on the on the screen for that day, and basically I will go, I will move the presentations forward. So we avoid like a sharing screen, one person, other person. I think this will make our our life a little bit easier. So also another thing that I want to mention is that I will not be able to record the presentations. So for those last four lectures, so when we do the presentations, the attendance is required. So if you can't attend, please let me know, but you should try your best to attend, because you will need to do the evaluation as well. So make sure that for the last four classes you can attend, because you will need to do a peer review for your classmates. Speaking about this, I'm going to share my screen now. Please share the screen. Share screen. So speaking about this, here I created this Excel file where we have on the first sheet the peer review, the rubric for the peer review. I don't remember if I uploaded already this one on Canvas. If not, I will do soon. But here you can see, all the criteria that you will need to use to evaluate, the other groups. And of course you can use this to prepare your own presentation to make sure that you do your best and meet all these criteria. Also, we will have 12 groups, so here I included 12 columns starting from column D to column O, and here in the second tab you will see the order presentation, which is what we did at the very beginning of the semester. I don't know if you remember, we did on Google. So here we have the list of the presentations, and we will fill this file column by column. So here you can see first presentation, second presentation, third presentation, and so on. So it will be a little easier, for everybody. Again, we will keep filling by column. Also, once you work on this one, make sure that you don't change anything. So make sure that you just put the numbers here. For this one will be between 0 and 25, for this between 0 and 15, and so on. So don't change the column, don't convert to PDF, don't do equations, anything, because I will create a small Python code to do the calculations, so I don't have to do by hand. But if you change something in this file, it will be a nightmare for me to figure out. So again, just put the numbers here and then submit the Excel file as is. Make sense? Any question so far? Very good question. So we will have 3 presentations per day, which means I would expect about 20 minutes, let's say, yeah, 20 minutes, and then we change from one group to one. Yeah, I would say about 20 minutes, 20, 25 at most. Yeah, because if you do, we have 1 hour and 15 minutes, so we can go up to 25, but probably if you stay within 20, that should be okay. Don't do a 5-minute presentation, please. So I think that would be like a reasonable number. So in those 20 minutes, we should have also, you know, a little bit of room for questions and answers. And I would like to see a lot of questions, and I'm sure there will be good answers to the questions. Make sense? Okay, sure. I think this is what I wanted to mention before moving forward. Is there any other question before we move on? Alright, I guess we can move on. So again, as I mentioned, I hope you had the chance to watch the class last time, but if not, we are going through a quick review of what we did last time. But still, if you didn't watch, please go ahead and watch the video. So last time we talked at the beginning a little bit about the transition, let's say, between 2 degrees of freedom and multiple degree of freedom system. We said that the transitions actually in this case is very easy. The only difference that we have between a 2 degree of freedom system and more than 2 degree of freedom system is pretty much the size of the matrices. So if we have a system with, let's say, 3 degrees of freedom, instead of having a stiffness matrix and mass matrix that are 2 by 2, as we saw for the 2 degree of freedom system, we will have matrices that are 3 by 3. When we look at the eigenvectors, instead of having 2 elements in the eigenvectors, we will have 3 elements in the eigenvectors. When we look at the equations in modal coordinates, instead of having 2 equations, we will have 3 equations. So basically, it's just a matter of scaling up what we already did when we were working with 2 degrees of freedom. So this transition should not be a big problem. Of course, when we work with systems that have more than 3 degrees of freedom, 4, 5, 6, and so on, we will need the help from some software to do, to go through all these, linear algebra, do all these matrix calculations. But the steps are very mechanical. We went through the model analysis steps, and we saw that again it's just a matter of having the equations of motion first, and then after we have the equations, we need to go through a bunch of linear algebra steps. Does it make sense? Alright, thank you very much. Then after that we did another transition, which is a transition between discrete systems, which are systems that are identifiable with concentrated masses connected to each other through flexible elements, for example the springs or the dashpots. So far we talked about these discrete systems that they can have more, 1, 2 or more degrees of freedom. Here we have the examples, so it can be a simple harmonic oscillator with the mass in the spring, or it can be the pendulum, or if we have 1 degree of freedom in both cases, or the car with the suspension. This is an example of 2 degrees of freedom, for example. And so when we move to continuous systems, we don't talk anymore about systems with lumped masses, but we talk about bodies that are flexible. So the most simple example is the example of a string that is connected between 2 points. So in this case we have again the string that can be deformed in any way we want, pretty much, and this deformation means that we have to introduce another variable. So again, the main difference is that we look at lumped masses versus flexible bodies. So I would say probably the most important consequence is that when we talk about discrete systems, the only variable as a solution of our displacement is the time. As a function, of our solution is the time. When we look at continuous systems, we work with differential equations whose solutions have two variables, which are time and space. Sometimes actually even more than two, if instead of looking at 1D system, if we look, for example, at 2D vibrating systems, for example a plate, in that case we would have one time variable and two space variables. So in that case it would be like 3 variables. For now we will focus only on 1D system, so which means we have one time variable and one space variable. Another difference is that the number of degrees of freedom is finite when we look at discrete system. The number of degrees of freedom is infinite when we look at continuous systems. This is because when we look at the deformation of this string, for example, every point can be considered as a degree of freedom. See, so if we look at the entire length, we have infinite points between the beginning and the end of the string. So it means that we have an infinite number of degrees of freedom, and this is why we have to approach the problem, with different tools. Another consequence is that the equations of motion, instead of being ordinary differential equations, are partial differential equations. This is because instead of having only time as a variable, we have time and space. This is what makes the equations partial differential equations instead of ordinary differential equations. And then we will talk about also the solutions. We will see today how to solve actually the wave equation for a string. Any question about these differences? All right. So we started to look at the most simple case of continuous systems, which is the case of the string. So the string vibration is governed by the wave equation. When we look at partial differential equations, we can use different notations to write them, and here I showed all 3 notations that can be used, but remember that all these 3 notations are perfectly equivalent. It's just different way of writing them. So we can have utt equal to c squared uxx, or second derivative of u with respect to t squared equal to c squared times second derivative of u with respect to x, or u double dot equal to c squared u double prime. Again, 3 equivalent notations. Wave equation, very important. It can be found in many different situations. Most common for acoustic, in this case this constant c would be the speed of sound, or in optics this constant c would be the speed of light. So and then after that we started by looking at a way to derive actually this equation. So we have our string that is between again point let's say A and point B. So this is the distance between the two points, which we can call L, which is basically the length of the string. And of course what we need to look at, so what we need to find is the displacement in the vertical direction. So this dotted line would be the undeformed configuration. The deformed configuration would be what we need to find, which is the displacement as a function of time, space and time. So how can we find the equation? We start from the Newton law. So we take one small piece of the string and then we make a few assumptions. The first one is that the gravity is negligible, so we don't consider the effect of the gravity if we have enough tension in the string. Also, we assume that we have small deflections in comparison with the entire length of the string, so at least one order of magnitude smaller. And then we also assume that we have uniform tension, so the tension doesn't change along the length of the string. So after that, again, now we can look at the forces that are involved. So we have the tension on one side, the tension on the other side. Remember, the value of this T is the same because we said we have only uniform tension. We also have certain orientation at these 2 points, so we use this angle theta to determine that orientation. We also introduce linear density, which is the ratio between mass and unit of length for our string. So from this linear density we can obtain the mass. So mass is equal to product between density and change in length. For this side of the equation we also need to determine the acceleration, which is a second derivative of displacement, and we can use UTT, or of course we can use other notations. So right hand side of the equation is m times a, which is rho delta x UTT. Regarding the left hand side of the equation, we can look at the summation of forces. So we have the forces on one side, the force on one side is the tension, the force on the other side is the tension as well, that are oriented in a different way depending on the angle of the string. We can replace, since we talk about small displacement, we can replace the sign with the tangent, and the purpose of this is to relate the horizontal change in length with the vertical displacement, and we can do that by looking at the ratio between these two quantities, which is basically the tangent. And then we can replace, so we know that the tangent is basically the derivative of our displacement with respect to time, because u, of course, would be in the y direction, it's going to be with respect to x, and then we can write the equation in this form. Now we can plug both sides of the equation here. We can rearrange a little bit, where we have rho delta x on this side. We know that we are talking about a very small, tiny piece of the string, so we can take the limit for delta x that goes to 0. When we take the limit for delta x that goes to 0, we are basically calculating the derivative of this function. This is already the derivative here, which means we are doing the second derivative. Since we are doing the second derivative, we can simply replace all these terms here with the second derivative of the displacement with respect to space, with respect to variable x. We said that t over rho is, we did a little bit of dimensional analysis. We know that t over rho is basically a speed squared, so we can replace this t over rho with c squared. Again, of course, depending on which system, which physical system we are looking at, this speed can be speed of sound, speed of light, and so on. We also said another thing, that when we look at this constant, t over rho, we can understand the parameters that have an influence on the vibration of the string. What are the two parameters? The tension that we have in the string, and what kind of string we have, which means what kind of material, what kind of linear density we have for the string itself. And I gave the example of the guitar. if you change the tension in the guitar, you will have a different sound. If you change the type of string that you use, you will also have a different sound. Make sense? So this is a quick recap of what we did yesterday. Any question? It depends. You can have different, and this is what we are going to talk about now actually. So when you look at continuous systems, you can have fixed supports or movable supports, or you can have supports on strings. You can have on springs. So this is something that will have an influence on your final solution, because if you change the support, what you change is the initial condition, basically. So exactly like we do for for discrete system, when we change the initial condition, which will be a certain amount of displacement, for example, or an initial velocity, when we change the type of support that we have for the string or for a beam or for a membrane, what you change are the boundary conditions, basically. Makes sense? Other question? Okay. Other questions? Alright, if there are no other questions, we can move forward now that we have the partial differential equation that is in charge of determining the vibration of a string. Now we can try to determine the solution to this partial differential equation. So I'm going to rewrite the equation here. So we can use this notation: UTT equal to c square uxx, where remember that square root of t over rho is c, and we already did the dimension analysis of this, so we know this is a velocity. Now there are different ways of solving equations like this. The way that we are using now is called the method of separation of variables. Now the goal of the method of separation of variables is somehow similar to the goal that we have when we use the model analysis. Does anyone remember what the goal of the model analysis is when we look at discrete systems? Why do we use model analysis? To determine that's correct. This is one part of, but we can determine the natural frequencies of the system even without the model analysis. So we can try to think at the main goal of actually going through all these steps of the model analysis. Well, this is similar to having the the natural frequencies, which are basically the resonance point. So I would say that the main goal of the model analysis is to have equations that are related to each degree of freedom that are not coupled to each other. If you remember, when we solved a 2-degree of freedom system for the first time, we ended up with two differential equations that were coupled. So that it is doable. We can solve this type of systems with assumptions, but when we go through the model analysis, at the end, almost at the end, we have two independent differential equations that were very, very similar each of them to the simple harmonic oscillator equation of differential equation. So now in this case, when we use a separation of variables, we are doing something similar, because in this case we have one single equation that whose solution has two variables, because the solution here, u, is a function of both x and t, so it's a function of both space and time. So we will use this method again of separation of variables so that we obtain two separate equations. One is only function of space, the other one is only function of time. That's why it's called separation of variables. Makes sense? So basically the purpose is to simplify our problem, simplify our equation, and make it similar to or equal to another equation that we already know how to solve, basically. Makes sense? So let's see how we can do this. Now, we said that this u, again, it's our solution, is the displacement, is a function of both x and t. So, function of both space and time. We also said that we need to give a little bit of context in our problem, and give a little bit of context means give like conditions, give boundary conditions in particular. So in this case we can start to think about the boundary conditions, because actually we will need these boundary conditions for the solution itself. So in terms of conditions for this problem, we can think about a string that is pinned on both sides. So it is pinned on both ends. Also, another thing that we should think about is that since we have that our solution is a function of both space and time, we are going to need both boundary conditions and initial conditions. So the boundary conditions will be related to the portion of the solution in space. The initial conditions will be related to the portion of the solution related to time. If you remember, when we were looking at discrete systems, we only had initial conditions. We only had initial conditions because we only had time as a variable, right? In this case, since we have both time and space, we need initial conditions and boundary conditions. So for this type of configuration, when the string is pinned on both sides, it means that okay, let me do this. It means that the string at each end can rotate but cannot go up and down. So for each point, for the two ends, there is no displacement. So if we call this x equal to 0, and if we call this x equal to L, the way how we are going to write the boundary conditions and initial conditions is as follows. So for the boundary conditions, again, that depend on space, we will have that our function for x and any time t is always equal to 0. we can also write that our function for x equal to L and also any time t is equal to 0. Does this make sense? So this means that when we look at our function, for sure, at the beginning, so for when x is equal to 0, and at the end, when x is equal to L, the displacement must be 0. There is no movement in the vertical direction for these 2 points because they're fixed. So this is what we can see in terms of boundary condition. In terms of initial condition, this kind of depends on what kind of shape, for example, we want to give at a certain time. So, for example, let's assume that we have our string, again, that is pinned at both sides, and at one point along the length of the string, we pull it and we give a certain displacement. So, for example, we can do something simple that looks like this. So at this point here, from the undeformed condition, we are giving a certain displacement, which means that basically we are giving a certain function of space. So this again, initial condition. So this initial condition can be translated mathematically as u of x0, so at the initial time it will be a generic function of space. Does it make sense? And of course, depending on where we pinch, let's say, a little bit our our string for the initial time, of course this function can change a little bit. So now that we talked a little bit about our conditions from a physical point of view and how we translate them in mathematical form, we can start to think about the solution. So we said that we are going to use the method of separation of variables. When we use the method of separation of variables, we have to make an assumption. So the very first assumption is that our solution, which is our u of xt, is actually a product of two functions. One is a function of time only, the other one is a function of space only. So we can write our solution like u of xt, again, as we said, as the product of two functions. One is we can call it like uppercase f of x only, and the other one we can call g, that is a function of time only. Yes. So here, because when we look at the boundary conditions, these are conditions that are related to specific points. Because you for sure know that at any time your displacement here and your displacement here will be equal to 0. So that's why they are called boundary conditions. So these are two conditions that are related to what's going on at this specific point and what's going on at this specific point. When you look at the initial condition, it means that you are basically removing the time, because you are saying, okay, let's see what happens at the beginning of my study, of my timeline, right? So at the beginning of your timeline, you can say, okay, for a certain point, I give a certain displacement. You can even give a certain velocity. But of course, since it is a continuous system, when you apply a displacement for one point, all the other points will be influenced as well. So that's why in this case, when you look at the initial condition, when you give again a displacement of one point, all the other points will be influenced as well. So you will need to determine a function for this initial condition. Makes sense? If you have movable supports, these are not valid anymore, and we will need to look at different type of boundary conditions, because you can have movable supports that, for example, have springs. So springs. So if you have a spring here, that spring will actually give back some force. Or you can have a movable support that moves following a certain function of time, for example. So that will make the problem significantly more complex, but it is doable. So you change how you define the initial conditions in that case. Make sense? Sure. So, okay, we are here where we can say that our function, our solution, is a product of two functions. One function of time only, the other one function of space only. Do you remember what we were doing when we were looking at continuous systems? And around this point, when we said, okay, we can think about one possible solution for our equation. Once we had like a general form of a solution, what did we do? We derived and then we plugged back in our equation to see if that satisfies our solution. We can do something similar here. So if we look at our equation, utt equal to c squared uxx, what do we need? We need the second derivative with respect to time and the second derivative with respect to space. So let's go ahead and we can calculate these two derivatives for this function here. So we have utt, so the second derivative in time, means that we have f of x that stays like this, doesn't change because it doesn't change with time, so f(x) multiplied by the second derivative of this function, which is a function of time. So we can call g double prime of t. Similarly, we can calculate the second derivative with respect to space. So we have uxx, which will be equal to f double prime x times g of t. So now that we have these two, the second derivative in time and the second derivative in space, exactly like we were doing before, we can plug them back in our initial equation. So we have fx times g double prime of t equal to c squared times f double prime of x times g of t. Now that we have this, we can actually do the separation of variables, because we can rearrange this equation and we can bring on one side whatever is function of x and on the other side whatever is function of t, so space and time. So if we do this, what we obtain is the following. We have f double prime of x divided by f of x is equal to 1 over c squared g double prime of t divided by g of t. So if you look at this that we have here, we basically bring this f double prime here, this g double prime here, or vice versa, we can bring this g under this one, this f under this one, and then what we obtain is this form of the equation. Any questions so far? Okay, I think now is the time to do a little bit of reasoning on what we have here, because the reasoning that we are going to do now is what will actually allow us to solve the equation. Because what we have here is, as we can see, on one side something that is only a function of space, on the other side something that is only a function of time, which means that in order to have these two functions equal to each other, they must also be equal to a certain constant. Because if there is one that changes only in space and there is another one that only changes in time, and if they are equal to each other, they must be equal to a third, let's say, constant. And this is because if, let's say, the left hand of the equation does not change with time, and this, the right hand doesn't change with space, in order to be the same to each other, because we now figure out that they are the same to each other, they must be constant, basically. They must be equal to the same constant. So this is basically the not tricky, but the reasoning that we have to do in order to actually find the solution of this. Now also we have to choose the appropriate constant that we are going to use here, and there are several options. Actually, we are going to use like a negative lambda squared, because this is gonna be useful in the next steps of this solution. So now basically what we have is not one equation anymore, but now we have two equations. One that is f double prime divided by f equal to negative lambda square, and the other one which is 1 over c square g double prime over g also equal to negative lambda square. Let me write that down so we can talk about this. So the first equation is f double prime of x divided by f of x equal to negative lambda square. The second is 1 over c square g double prime of t divided by g of t equal to also negative lambda square. So this first equation is only function of time. Excuse me, only function of space. Because here we only had the variable x. This one, of course, is only function of time. I don't know if you remember, at the beginning we said, okay, the goal of the method of separation of variables is to split our equation that has two variables in two equations where each equation has only one variable. And this is actually what we obtained, because we started from this equation here, where we have both time and space, to two equations where each has only space or only time. And I think this actually simplifies our problem significantly, because now we can we can kind of rearrange these equations here and we can start to solve them with more simple methods. So if we take this first equation, we can rewrite this one as f double prime of x plus lambda square times f of x equal to 0. So now again we are looking at this equation only, so we need to worry about x only, we don't need to worry about anything else. So we can think about a general form of this solution here. The general form of this solution here, if we again think back about the boundary conditions, because this is in time, so in space, so it means we have to look at the boundary conditions. Remember, the boundary conditions are telling us that there is no displacement at any time at one point, which is the beginning, and no displacement at any time on the other side, like at the end of the string. So we have to think about some function that can satisfy this type of conditions, and of course it must be some sort of sinusoidal function, and the period of this sinusoidal function should be equal to the length of the string, which is the distance between these 2 points, the initial and the final point. So in general, we can write our f of x as a certain constant. We can use for example beta times sine of lambda x. Again, it can be, the solution of this equation is not only one solution. There are like multiple functions that can satisfy this equation, as considering the boundary conditions. As long as we have no displacement at the beginning and at the end, because of the boundary conditions, we need to have one sinusoidal function that has basically 0 and 0 at the beginning and at the end. So just to start to think about this, the solution can be, for example, if this is the initial point and this is the final point, the solution can be something that looks like this, or can be something, for example, that looks like this. These two functions satisfy, or can be something, for example, that looks like this, and so on. All of them satisfy. How do we bring this? By having this lambda here, which is basically a multiplier of our frequency. So this number here, lambda, again must be related to the length of the string, so a distance between the initial and the final point. So we can write this as a lambda equal to pi over L times n, where n is the actual multiplier that will give us every possible solution, which means every possible shape of the string excuse me, every possible shape of the string that satisfies the initial condition. So n can be 1, 2, 3, and so on. So if we plug this here, we have that our function f of x will be equal to our beta that is specific for that n that we select, times sine of n pi over L times x here. So this is the function that we have, see the solution that we have in space. Now we can think about the solution in time. So we start, of course, from this, which is the equation that takes time only into account. So we can rearrange this one as follows. So we have g double prime equal to negative c square lambda square g. Of course, we can bring everything on one side of the equation. So we have g double prime plus c square lambda square g equal to 0. So even in this case, the function is not much different from the function from the equation that we had before. We have only this difference, that we have c squared times lambda square as a multiplier for our function g. So the solution is also some function of sine and cosine. So in general we can write that our solution g of t is equal to, let's say, a certain constant, let's say uppercase k times cosine of c lambda t plus we can use another constant, let's say j, and then sine of c lambda t. Now, even in this case, we have to do a little bit of reasoning, and we have to look at the conditions. In this case, we look at the initial conditions. For this one, we were looking at the boundary conditions. For this one, we have to look at the initial conditions because we are looking at time. From the initial conditions, also we saw that, for example, for the initial conditions, we saw that here we also don't have displacement, and then we have a certain displacement along a certain point of x. So in order to satisfy this one, we can look at the cosine term only. So we can write our g, can simplify our g of t as k cosine of c lambda t. And even in this case, of course, we can look at certain sinusoidal and multiplier for this lambda, which is the one that we found before, because lambda is always the same. It comes from the same constant that equates the two functions. So we can rewrite this one as g of t equal to k n, because again it repeats, cosine of n pi over L c t. Yeah, I don't know why it goes out of focus. Okay. So now, again, after a little bit of reasoning, looking at the initial conditions and the boundary conditions, we found the solutions for the two variables. We said that our function, like u of xt, is a product between these two. So now we can take this one, and we can put them together to find the u of xt. We also said that basically this is not only one solution that satisfies the initial and boundary conditions. So instead of having simply the product between these two functions, the f of x and the g of t, what we are going to look? We are going to look at a summation of the product between these two, and then what we have to change is the value of n, because we introduced this parameter n, because we said that again we have multiple solutions that can satisfy multiple functions that can satisfy our function, our equation. So we can write u of xt as summation for n that goes to 0 to infinite of c n sine of n pi over L times x and cosine of n pi c over L times T. So now let's try to do a little bit of reasoning, of physical reasoning of this one, because we always look at the equation, but for us the most important part is to look at the physical meaning of all these equations. So of course we were looking at a function which is a displacement, and see how this displacement changes with space and time. We found this summation where we see a lot of parameters involved. Of course we see our variables x and t. We also see that we have sine and cosine functions, which make sense according to the boundary and initial conditions, so the physics of the problem. Of course other parameters that are involved are the length of the string. As you can imagine, if we change the length of the string, we are going to see some difference in how it vibrates. And then we also have these two parameters, this Cn and this C. Now this Cn is a constant that is determined by the initial and the boundary conditions, because this Cn is something that came from the calculations that we were doing before. And also we have this other parameter C, which is what we also defined at the very beginning, that's C squared. So this C is the ratio between the tension and the linear dimension, the square root of the ratio between the tension and the linear dimension. So of course the solution depends on how much tension you have on the string and what type of string you have, like the material of the string. This term n here indicates which term of the solution we are looking at, because when we change this n, the shape of the solution will change as well. And if we try and we replace 1 and then we replace 2 and then we replace 3, we will see different solution. Each of these n, so n equal to 1, equal to 2, equal to 3, correspond to a specific mode of vibration of the string. So n equal to 1 will give us the first mode of vibration. N equal to 2 will give us the second mode of vibration. N equal to 3 will give us the third mode of vibration, and so on. Of course, since it is a continuous system, we have infinite degrees of freedom, and also this n will go from 0 to infinite. We will have infinite modes of vibration, and each mode of vibration will correspond to a specific deformation, to a specific pattern of deformation of our string. In addition, another thing that we can say is that this number n, so if you look at n equal to 1, n equal to 2, n equal to 3, and so on, will give us the number of what they are called nodes and antinodes. So for example, when n is equal to 1, so for the first mode of vibration of the string, if we plot this, of course, assuming that we know the length of the string and also the type of string, the material, again, from a qualitative point of view, we will see something that looks like this. If n, so let's try to stay consistent, the same length, so for n equal to 2, the shape would look like this. If n is equal to 3, again, same length, the deformation would look like this, and so on. If n is equal to 4, let me try with this one, this one. the deformation will be like this, and so on. We can keep going up to n equal to infinite. As you can see, there is a kind of pattern, because when we increase the value of n that we would replace here in the equation, what changes is the number of nodes, which is the number of points that doesn't move, even if all the other points actually move. So for example, in this case, for n equal to 1, we have 2 nodes and 1 antinode. For n equal to 2, we will have 3 nodes and 2 antinodes, and so on. So basically, when we look at the specific mode of vibration, so for the first one, when n is equal to 1, the number of nodes is 2, antinodes is 1. So basically, the number of antinodes, which is the location where we have the maximum displacement, will be equal to the mode that we are looking at. The number of nodes will be equal to n plus 1, because here, for n equal to 2, we have 2 antinodes and we have 3 nodes, so 3 will be equal to 2 plus 1, so it means that the number of nodes is equal to n plus 1. Same thing here, we will have 1, 2, 3, 4 nodes, which is 4 equal to 3 plus 1. Same thing here, for n equal to 4, we have 1, 2, 3, 4, 5 nodes, which means that we have, of course, n plus 1 number of nodes. So I give you like a couple of minutes to kind of think about this. Last semester I did actually a demonstration in class, I mean last year, when I taught this class before, with a string and different and a shaker to give some input. We cannot do this online, but I will try to find some video that shows how the vibration of a string is influenced by the input, and when we look at the different nodes. So, questions? That's a phenomenal question. Thank you for asking. So, when we look at these, usually for vibrating systems, from an engineering point of view, the most important parameter, especially from a structural engineering point of view, the most important parameter we should look at is the amplitude of vibration. We already said when we were looking at discrete systems that we don't want to have a vibration that is like too big, because if you have a material that is vibrating with an amplitude that is too big, it means that you have big strain. If you have too much strain, you may go to to plastic deformation, and eventually you can go to actually failure of the material. So now, if you look at the displacement, at the amplitude of displacement, it decreases when we move from mode 1 to mode 2, mode 3, and so on. This is the same that happens when we look at a discrete system, but in particular for continuous systems, when we look at all the amplitude of vibration, we can see that the first mode is the one that has the highest amplitude of vibration, typically. So we need to look at those that have the highest amplitude of vibration. Again, because from a structural point of view, we don't want to have too much strain. Make sense? Other questions? Mm-hmm. Mm-hmm. Typically, yes. If you look, if you want to look like at a analytical solution of systems, we can, for example, next time I'm planning to give you a little bit of introduction. We're not going to be able to go through the entire derivation and solution for a beam, which is like the next system that comes after a string in terms of complexity. So if you look at the vibration of a beam, let's say a cantilever beam, and a wing, unless you have some brace, can be like modeled as a cantilever beam, pretty much. So even in that case, depending on what type of external force you have, if you have an external force, and depending on how that external force is applied, so if you change the frequency of that external force, you may have like a different amplitude of vibration. And typically when you increase that frequency of excitation, you have a decrease of the amplitude. So generally depends on what you should do. You should look at the natural frequencies that come from, again, all these modes basically of vibration. And then when you go to the first mode, you typically have the higher amplitude. If you look at the second mode, you have a smaller amplitude. So in general, for structural analysis, you don't want to go even closer to the first mode of vibration, because it's the one that gives you the highest amplitude of vibration. So you always want to stay very far away from the first mode of vibration, because again, it's the one that gives you the highest amplitude of vibration. Again, hopefully next time we will have chance to go quickly over like all the talk a little bit about beams. Sure. Other questions? Alright, if there are no questions, with the last 4 minutes, we are done for today, and we are going to meet again next Monday. And again, we will go over a little bit. We will try to see what we have to do when we have a beam instead of a string, and when the beam is subjected to a certain transverse vibration. Alright, I can stay here a few more minutes if there are questions, but if not, again, we are done for today, and we are going to meet next week. Alright, thank you very much, have a good night. Alright, sure. Sure. I think I can close the recording. We are done.